Hello everyone, today Group 4 are going to share about the concept of displacement current. Before we start, here are our group members. We have BAALA MURUGEN, Henry KANG, JIAN, SESSHARTAN, and me, HENG.
Hi all, I am SESSHARTAN and today I am going to explain about the introduction to displacement current concept. So, what is displacement current? Electricity and magnetism are related to each other. As the electric current travels through a wire, it creates magnetic field lines around the wire. This type of current is called conduction current, which is created by the movement of electrons through a conductor such as an electrical wire. Displacement current is the current that is produced by the rate of change of the electric displacement field. It differs from the normal current that is produced by the motion of the electric charge. Displacement current is the quantity explained in Maxwell's equation. It is measured in ampere, and displacement currents are produced by a time-varying electric field rather than moving charges. In this video, we will learn about displacement current, its characteristics, and others in detail. So, displacement current can be explained based on this phenomena where how can the current go through the dielectric material. So, the displacement current definition is a physical quantity related to Maxwell's equation that has the property of the electric current is called the displacement current. Displacement current is defined as the rate of change of the electric displacement field. So displacement current also can be explained based on the current in capacitor, where a charging capacitor has no conduction of charge, but the charge accumulation in the capacitor changes the electric field link with the capacitor that in turn produces the current called the displacement current. And this displacement current can be explained based on two laws, which is Ampere's law and also Maxwell Ampere law. Ampere's law was developed by Andre Marie Ampere. It states that when conduction current passes through a closed loop, a magnetic field is formed around the closed loop. So here, Maxwell gave an addition to this law which resulted in Maxwell-Ampere law. So James Clerk Maxwell, a famous physicist well known for his work on Maxwell's equation, gave addition to Ampere's law which stated that magnetic fields can be generated in two ways, by electric current and by changing electric fields. So this is some additional info about James Clerk Maxwell. So here are some basic explanation on the equation of Maxwell-Ampere law. Maxwell predicted that a time-varying electric field in a vacuum or free space produces a magnetic field. It indicates that a changing electric field causes a current to flow across a region. Maxwell also predicted that this current produces a magnetic field similar to that of a conducting current. Displacement current was the name given to this current, and the characteristic of displacement current are it does not appear from the actual movement of the electric charge as in the case of the conduction current, but is produced by the time-changing electric field. Displacement current is also a vector quantity and its SI unit is ampere. Electromagnetic waves propagate with the help of the displacement current.
Maxwell equations are a set of fundamental equations in classical electromagnetism that describe how electric and magnetic fields interact. They were formulated by James Clerk Maxwell in the 19th century and are crucial for understanding the behavior of electromagnetic waves, including light. One of the key equations in Maxwell's set is the equation related to displacement current. The displacement current term was introduced by Maxwell to complete Ampere's law, which relates magnetic fields to electric currents. Ampere's law, in its original form, did not account for certain situations, particularly those involving changing electric fields. To address this limitation, Maxwell added a new term to Ampere's law, known as the displacement current.
Now, let us discuss on the description on Maxwell equation to displacement current. From continuity current equation, we know that the divergence operator of current density is equal to the negative of differentiation of volume charge density. Besides that, we also know that the charge density is equal to the divergence operator of magnetic field intensity, and the volume charge density is equal to the divergence operator of electric flux density. Therefore, the final equation is equal to the last line of this. By vector identity, the left-hand side is equal to 0. So we need to add one more differentiation of volume charge density. And next, we can cancel out one divergence operator. And the second line of equation is the Maxwell equation to displacement current. Maxwell equation to displacement current is the convergence operator of magnetic field intensity equal to the conduction current density plus the differentiation of the electric flux density. For a perfect dielectric, current density is equal to 0, and the convergence operator of magnetic field density is equal to the displacement current density. Displacement current density means that the current flow in the dielectric material of the capacitor. And this is the description of the Maxwell equation to displacement current.
The first equation here is the Maxwell's equation based on Ampere's current law for a time-varying field. The term JD equals to delta D over delta T is known as displacement current density, and J is the conduction current density. The insertion of JD into the equation was one of the major contributions by Maxwell. Without the term JD, the propagation of electromagnetic waves such as the radio or TV waves would be impossible. At low frequencies, JD is usually neglected compared with J. However, at radio frequencies, the terms are comparable. As we can see here in the second equation, based on displacement current density, we define the displacement current as ID equals to the surface integral of JD dot ds, which is also equal to the surface integral of delta D over delta T dot ds. We must bear in mind that displacement current is a result of time-varying electric field. A typical example of such current is the current through a capacitor when an alternating voltage source is applied to the plates.
Okay, so now I'm going to talk about real-life applications for displacement current. So one of the common applications is antenna for signal transmission and also reception. Heinrich Hertz is the first person to transmit and detect magnetic wave in the early century. So during his experiment, a high voltage is applied to two metal rod ends, and the spark is produced in the gap. This spark results in radiations of electromagnetic wave which travel through air and result another spark at the metal coil placed a few meters away from it. So the problem statement is, from the previous lecture, we know that the electromagnetic field is located around the wire, but during electromagnetic wave propagation, electromagnetic field detach themselves from the wire. So how does this happen? To explore it logically, we consider an electric charge with a constant speed. So this is the electric field. In the fractions of second, it accelerates and continues its uniform motions at a higher speed. This causes that the electric field away from the charges cannot respond to it. So now we have two different electric fields. One is the electric field that near to the charges, and another one is the electric field that far from the charge. And we know that electric field is non-breakable, so that the transmission between these two electric fields is called kinks. And kinks is the radiations of electromagnetic wave. In summarize, we know that accelerations of charges causes electromagnetic radiations. So after understanding what is electromagnetic radiations, we're going to move to the most important experiment in antenna technology, aka oscillating electric dipole, which produce perfect sinusoidal electromagnetic radiations. So at the initial state, the velocity is 0, and this is the electric field that produced by these two charges. So when time increases, we can observe that the electric field line is deformed. This is because at this time, the charges experience accelerations. And the wave deformations is continuous since there is continuous accelerations of charges. When the charges meets together, the deformed line also meets up. When the deformed lines meets together, they will detach and radiate. So now we're going to see how this happened to an antenna. So this is a basic setup of an antenna, which consists of a time varying voltage and two metal rods. So when the voltage is supplied, uh, electron will move from one end to another end, which produce positive and negative charges. With the variations of the voltage, the polarity will changes. Thus, when there is a changing of polarity, electromagnetic radiations occur. And this is how we transmit our electromagnetic wave. Thank you.